The sun sits 93 million miles away. Mostly it just burns. But sometimes the burn becomes a blast. A magnetic field snaps. Billions of tons of plasma rip loose. The solar wind turns into a solar hurricane. And when that hurricane points at Earth, the consequences reach down to telegraph wires catching fire, power grids collapsing in 90 seconds, satellites tumbling blind, and astronauts scrambling for shielded compartments as radiation counts climb past levels that can kill. Every storm has a different signature, different speed, different payload, different path through our magnetic shield. Some storms blind us with X-rays, others send protons screaming at near light speed. Some twist our magnetic field until transformers overheat. Some carve their signatures into tree rings for us to find 14,000 years later. Which type hits hardest? How many have we survived without knowing? What happens when the big one arrives during a world that runs on satellites and chips? The Quebec storm that killed power for 6 million people in less than 2 minutes. The Halloween flares that temporarily lost half our orbital hardware. The radiation blasts that force astronauts into storm cellars. The ancient carbon spikes so massive, they rewrite our assumptions about what the sun can do. Every number here comes from instrument records, ice cores, tree rings, or damage reports filed with insurance companies. This is what the sun has already done. This is what it will do again. 1004, NASA's Goddard Space Flight Center Heliophysics Division. Technical papers on the May 2024 Geomagnetic Storm Disturbance Storm Time Index measurements showing negative 412 nanoteslas. Peer-reviewed articles in Nature Communications by Fusa Miyake and co-authors documenting the 774 to 775 carbon-14 spike in Japanese cedar tree rings, published June 2000. 12, and David Boatler's 2019 Space Weather Journal analysis of the March 1989 magnetic storm using revised coronal mass ejection transit time calculations. These aren't pop science summaries. These are the primary data publications that space weather forecasters actually use. Now, back to the information. Redhill, outside London. Richard Carrington aims his brass telescope at a cluster of sunspots. The sunspots are massive, 10 times Earth's diameter. Then 2 patches of intensely bright white light erupt from the cluster. The light burns so bright, Carrington thinks his filter cracked. 5 minutes. The flares vanish. Carrington sketches what he saw. He has no idea he just witnessed the most powerful solar flare ever directly observed by human eyes. 17.6 hours later, the blast wave hits Earth's magnetic field. Speed, approximately 1,900,000 miles per hour. The leading edge of the first coronal mass ejection cleared a path through the solar wind. The second coronal mass ejection hit like a freight train through an empty tunnel. Earth's magnetosphere compressed, magnetic field lines tangled. The result released an estimated 10 to the 35th electron volts of energy. That's the energy equivalent of 10 billion atomic bombs the size dropped on Hiroshima. Another telegraph operator in Pittsburgh noted that his equipment was sending messages without batteries. The geomagnetically induced currents flowing through the ground were strong enough to power the system. Telegraph networks in Europe experienced similar chaos. Wires glowed, insulation melted. Approximately half of all telegraph stations in the United States reported equipment damage or temporary loss of service. But the most spectacular effect was the aurora. Red and green curtains of light blazed across the sky from the Arctic to the Caribbean. People in Cuba saw auroras. People in Panama saw auroras. Gold miners in the Rocky Mountains woke at 1 a.m. thinking the sun had risen because the sky glowed so bright. People in New York read newspapers by aurora light at midnight. Birds in England began singing, confused by the false dawn. The magnetic storm was so intense it created electrical currents in the ground across most of North America and Europe. Compasses spun, magnetometers went off scale. The Kew Observatory in London recorded a magnetic disturbance so large the instruments couldn't measure it accurately, to negative 1,750 nanoteslas. For context, a strong modern geomagnetic storm registers around negative 100 nanoteslas. The Carrington event was between 8 and 17 times more powerful than what we currently classify as an extreme event. Ice core analysis later confirmed matching spikes in beryllium-10 and chlorine-36 isotopes created when solar protons bombard Earth's upper atmosphere. If a Carrington-class storm hit today, the economic damage would range from $600 billion to $2.6 trillion in the United States alone, according to a 2013 joint study by Lloyd's of London and Atmospheric and Environmental Research. That figure represents 3.6 to 15.5% of annual GDP at the time of the study. Power transformers would overheat. Grid cascades would darken entire regions. Satellites would tumble. GPS would fail. High-frequency radio communications would black out. The storm would take months to years to fully repair. We got a preview in 2012. The blast missed our planet by roughly 9 days of orbital motion. Stereo. A spacecraft, positioned ahead of Earth in its orbit, took the hit instead. If Earth had been in that position, we would have experienced a repeat of 1859, but with a modern grid that depends on chips, transformers, and satellites. We got lucky. Next time we might not. Solar cycle 22 was reaching its peak. Sunspot region 5395 grew to enormous size on the sun's surface. March 6th, an X-15 class solar flare erupted. March 10th, a coronal mass ejection launched. March 12th at approximately 0200 hours universal time. A second, faster coronal mass ejection blasted outward. The first coronal mass ejection cleared the path. The second accelerated through the gap. Transit time of the first shock, 54.5 hours. Speed, 760 kilometers per second. Transit time of the second shock, 31.5 hours. Speed, 1,320 kilometers per second. In space, NASA's TDRS-1 communication satellite recorded over 250 anomalies as high-energy particles invaded its electronics. The Space Shuttle Discovery, in orbit during the storm, suffered a sensor malfunction. A hydrogen fuel cell pressure sensor showed unusually high readings. The problem disappeared after the storm subsided. Some satellites in polar orbits lost attitude control for several hours. But the real damage happened on the ground. Quebec sits on the Canadian Shield, a massive expanse of Precambrian igneous rock. The rock is electrically resistant. When geomagnetically induced currents try to flow through the ground during a magnetic storm, they find a better path, the power lines. Hydro-Quebec operates very long transmission lines running north-south across the province. Distance from James Bay to Montreal, approximately 1,000 kilometers. The longer the conductor, the more voltage a changing magnetic field induces. At 2:45, 5 transmission lines from James Bay tripped offline simultaneously. Generation loss, 9,450 megawatts. Total system load at that moment, 21,350 megawatts. The grid couldn't withstand a sudden loss of nearly half its generation. The entire Quebec power grid collapsed in less than 90 seconds. No power for the Montreal Metro during morning rush hour. Dorval Airport shut down, schools closed, businesses closed. The blackout lasted 9 hours for most of the province. Some essential equipment on the James Bay transmission network remained offline even longer because the blackout itself damaged components needed for restoration. Total power lost, approximately 19,400 megawatts in Quebec plus 1,003. 125 megawatts of exports. An additional 625 megawatts from isolated generating stations also went dark. Fortunately, none of the American problems caused a widespread blackout, but the margins were thin. Engineers later estimated that if any of several key transformers had failed, cascading blackouts could have darkened regions far beyond Quebec. That makes it the strongest geomagnetic storm of the space age, as measured by that metric, stronger than the 2003 Halloween storms, stronger than the May 2024 event. The storm's geostationary orbit proton flux peaked above 10 million electron volt thresholds. The K-index, which measures magnetic disturbance on a 0 to 9 scale, hit 9. The A-index, which averages K-index values, reached 240. Anything above 100 is considered a severe storm. They modified operating procedures to reduce power flows during storm warnings. Today, engineers believe Quebec's grid could withstand another March 1989 level event. But a Carrington-level event? That remains uncertain. Instead, 3 massive sunspot groups erupted on the sun's surface. The largest, Region 486, measured over 13 times Earth's diameter. Between October 19th and November 5th, the sun produced 17 major flares. 12 came from Region 486 alone. The X-ray flux saturated the GOES satellite sensors. Later mathematical modeling estimated the actual peak at X28, but the flare was so powerful it overwhelmed the instruments designed to measure it. The flare produced radio bursts near 245 megahertz, exceeding 500,000 solar flux units. That's one of the largest radio bursts ever recorded. A full halo coronal mass ejection followed immediately. Speed, over 2,000 kilometers per second. The geomagnetic storm jumped immediately to G5, the highest level on the NOAA scale. Aurora displays erupted across the northern hemisphere. People in Texas saw the lights. People in Florida saw the lights. People in the Mediterranean saw the lights. An X10 solar flare erupted from region 486, again followed by a powerful Earth-directed coronal mass ejection. The second storm arrived, while the first was still raging. The combined assault drove the disturbance storm time index to negative 353 nanoteslas at its peak. The geomagnetic storm maintained G5 conditions for 27 hours straight. then briefly subsided before the second pulse kept it going. Another 24 hours. Fortunately, Region 486 had rotated to the Sun's western limb by that point. The flare's energy blasted mostly away from Earth. The associated coronal mass ejection only triggered a moderate geomagnetic storm. The $640 million ADEOS-2 spacecraft, launched just a year earlier by the Japan Aerospace Exploration Agency, failed permanently. On board was NASA's $150 million SeaWinds instrument. Total loss: SOHO, the Solar and Heliospheric Observatory, temporarily went into safe mode. The Advanced Composition Explorer satellite suffered damage from the severe radiation. Half of all satellites in low Earth orbit experienced problems. Many lost tracking temporarily, requiring days of around-the-clock work to re-establish their positions and orientations. Star tracker cameras aboard multiple satellites were blinded by the proton bombardment, causing bright streaks and noise across their images. The module's thicker shielding provided better protection from the elevated radiation levels. NASA had only ordered such a retreat twice before in the station's history. Airline flights over the polar routes were rerouted or delayed to avoid exposing passengers and crew to increased radiation doses. Antarctic research stations lost all communications for over 5 days. GPS systems used for surveying, deep-sea drilling, and precision agriculture experienced degraded accuracy. High-frequency radio communications failed across large sections of the planet. The fact that transformers failed there demonstrates how powerful the Halloween storms were. They didn't just affect high-latitude regions, they reached far toward the equator. The storms also damaged satellite solar panels, reducing power generation efficiency on multiple spacecraft. Some satellites experienced phantom commands as radiation flipped bits in onboard computer memory. The Halloween storms demonstrated that extreme space weather can occur late in the solar cycle, not just near solar maximum. They showed that multiple coronal mass ejections can arrive nearly simultaneously, creating compound effects worse than any single event. They proved that modern technology is more vulnerable to solar storms than the relatively simple telegraph systems that failed during the Carrington event. And they provided a wake-up call that, despite decades of monitoring, we still have gaps in our ability to predict, prepare for, and respond to extreme solar weather. But there's another category of solar storm that poses different threats: solar radiation storms, also called solar proton events. These occur when magnetic eruptions on the sun accelerate charged particles, primarily protons, to extremely high velocities. The fastest protons can reach Earth in 30 minutes or less, traveling at significant fractions of light speed. No AA classifies solar radiation storms on a scale from S1 to S5, based on proton flux measurements at geosynchronous orbit. The scale is logarithmic. An S1 storm means 10 million electron-volt proton flux, exceeds 10 particles per square centimeter per second. S2 requires 100, S3 requires 1,000, S4 requires 10,000. S5 requires 100,000 particles per square centimeter per second, with energy above 10 million electron volts. The higher the flux and energy, the deeper the protons penetrate into spacecraft, atmosphere, and human tissue. Several hundred rem of radiation depending on exposure duration. That's enough to cause severe radiation sickness, a 10 to 20% risk of death in the short term, and a 5 to 10% increase in lifetime cancer risk for survivors. During Apollo missions, NASA got lucky. No major solar proton events occurred while astronauts were on the moon or in transit. If one had erupted during a lunar surface excursion, the crew would have faced a medical emergency with limited options. Station. Water storage tanks provide additional protection. Water is an effective proton shield. Mission planners for future lunar and Mars missions are designing dedicated storm shelters with extra shielding, specifically for crew protection during solar proton events. Region at 50 to 80 kilometers altitude. This enhanced ionization absorbs radio signals that would normally reflect off the ionosphere for long-distance communication. During severe solar proton events, all ionospheric radio communications through polar regions can be completely blocked. Flights on transpolar routes experience radio blackouts. Emergency communications become difficult. Airlines sometimes reroute flights to lower latitudes or cancel them entirely during extreme events. They blind star tracker cameras with bright streaks, making it difficult for satellites to maintain proper orientation. Long-duration exposure to repeated solar proton events slowly degrades spacecraft systems, reducing operational lifetime. Some satellites carry redundant systems, specifically to handle proton-induced failures. Commercial transpolar flights operate at altitudes where some protection from the atmosphere remains, but during severe solar proton events, radiation levels increase noticeably. Pregnant women, frequent flyers, and flight crews accumulate higher lifetime doses. International guidelines from the International Commission on Radiological Protection recommend monitoring and limiting occupational exposure. During extreme S5 events, some airlines reduce flight altitudes or reroute to lower latitudes to minimize crew and passenger exposure. Neutron monitors. Since systematic monitoring began in the 1940s, only 77 ground-level enhancements have been recorded. The strongest occurred on February 23, 1956. Recent major ground-level enhancements include events in September 1989, July 2000, October, November 2003, January 2005, and December 2006. November 11th, 2025, an X5.1 solar flare erupted from active region 14274. Proton flux surged. The event produced the 77th ground level enhancement in the record. ESA spacecraft detected the particle event immediately. Satellites in low Earth orbit measured temporary enhancements of high-energy protons at the poles. Swarm constellation satellites observed proton-induced noise in their star tracker systems. Despite the intensity, no spacecraft were damaged, and no critical infrastructure on Earth reported failures. But the event demonstrated that ground-level enhancements continue to occur during the current solar cycle, and each one poses potential risks to aviation, spacecraft, and technology. Geomagnetic storms provide some warning time because the coronal mass ejection takes hours to days to reach Earth. But the fastest solar protons arrive in 30 minutes. Forecasters detect the associated solar flare almost immediately at light speed, but the particles follow close behind. That leaves very little time to issue warnings and for operators to take protective actions. Improved forecasting models are working to extend warning times, but the physics of particle acceleration during solar eruptions remains complex and not fully understood. Anything in modern history, these ancient solar superstorms leave signatures in carbon-14, beryllium-10, and chlorine-36 concentrations that spike suddenly in a single year, indicating massive influxes of cosmic radiation. While analyzing tree rings from Japanese cedar trees, in the annual rings corresponding to 774 to 775 Common Era, carbon-14 levels jumped by approximately 1.2%. That's about 20 times higher than normal year-to-year variation. It's the largest and most rapid rise in carbon-14 ever recorded. Other researchers quickly confirmed the spike using tree ring data from Germany, Russia, the United States, Finland, and New Zealand. The signal was global. It featured a sharp increase followed by a slow decline, consistent with an instantaneous production of carbon-14 in the atmosphere, followed by gradual absorption into Earth's carbon cycle. Ice core analysis from Antarctica showed matching spikes in beryllium-10 during the same time period. Beryllium-10 is produced by cosmic ray bombardment of the atmosphere, similar to carbon-14. The correlation between carbon-14 in tree rings and beryllium-10 in ice cores strongly suggested a solar origin. Possibly 20 times stronger. If it happened today, it would devastate modern technology. Satellites would fail, power grids would collapse, communications would black out, the economic damage would likely exceed anything humanity has experienced from a natural disaster. The carbon-14 spike was about 60% the size of the 774-775 event. Still massive. Still far beyond anything recorded by modern instruments. Historical records from that period are sparse, but the Anglo-Saxon Chronicle mentions a red crucifix seen in the sky after sunset in 774, possibly an aurora. However, no clear eyewitness accounts exist for auroras in 993. Either the events produced limited visible effects at mid-latitudes, or the records simply didn't survive. 6D before Common Era, 774 to 775 Common Era, and 993 to 994 Common Era. That's roughly one event per 1,000 years on average, though the spacing is regular. 14 spike dating to approximately 12,350 before Common Era during the late Paleolithic period. The spike was twice the size of the 774-775 event. Beryllium-10 analysis from Greenland ice cores showed a matching spike at the same time. This ancient superstorm was approximately 18% more energetically powerful than the next strongest known event, after accounting for differences in atmospheric carbon dioxide levels and Earth's geomagnetic field strength at that time. Alternative hypotheses include superflares from the Sun, supernova explosions from relatively nearby stars, or gamma-ray bursts. The lack of corresponding optical observations in historical records for the 774 and 993 events complicates the picture. Surprisingly, the researchers found no clear correlation. Some events occurred near solar maximum, others at solar minimum, others during mid-cycle. This lack of synchronization with the solar cycle challenges the conventional solar flare hypothesis. The study also found that some Miyake events appeared to last 1 to 2 years, rather than occurring as instantaneous bursts. This extended duration doesn't match typical solar flare profiles, which last minutes to hours. Another complication, Miyake events show no clear dependence on latitude in their isotope signatures. If solar protons entered primarily through the polar regions, as they do during modern solar proton events, you might expect stronger signals at high latitudes. The data doesn't clearly show this pattern. Events roughly once per millennium. The most recent confirmed event was in 993, over 1,000 years ago. Statistically, we're overdue for another. Some researchers estimate the probability of a Miyake scale event in the next decade at around 1%. That sounds low, but it's not zero. And because we've never observed one directly with modern instruments, we don't fully know what the impacts would be. Imagine a Miyake event hitting today. Satellite constellations would take catastrophic damage. Thousands of satellites could fail simultaneously. GPS would go down globally, communication satellites would fail, Earth observation satellites would be lost. The International Space Station crew would face life-threatening radiation exposure even inside the station. Astronauts on the Moon or en route to Mars would likely die without extremely heavy shielding. Power grids worldwide would experience geomagnetically induced currents, far exceeding anything transmission systems are designed to handle. Transformer failures would cascade. Entire continents could lose power for weeks or months, while the utilities source replacement transformers, which take over a year to manufacture. High-frequency radio communications would black out completely at all latitudes. Airlines would lose long-distance communication. Ships at sea would lose contact. Internet infrastructure, which relies partly on high-frequency backup links, would experience widespread disruptions. Even fiber optic networks, which are immune to electromagnetic effects, depend on powered amplifiers and routers that need electricity from the vulnerable grid. The financial system would face massive disruptions. GPS timestamping, which synchronizes transactions globally, would fail. Communication between financial institutions would degrade. Automated trading systems might trigger unpredictable cascades. The economic impact could reach tens of trillions of dollars globally. Modern space weather forecasting can give us hours to days of warning for coronal mass ejections once they leave the sun, but we don't know what precursor signs to look for that would indicate a Miyake-scale eruption. We don't know if they're associated with unusually large sunspot groups, unusual magnetic configurations, or something else entirely. We can't say with confidence whether they're purely solar in origin or involve some other mechanism. Until we understand the physics better, we're flying blind. For example, wooden construction elements from the Viking archaeological site at Lanceau Meadows in Newfoundland were dated by identifying the 993 Common Era carbon-14 spike in their tree ring sequence. The analysis showed the wood came from a tree felled in 1021 Common Era, definitively confirming Viking presence in the Americas before 1021. Similar dating techniques have been applied to building timbers, shipwrecks, and other artifacts. Can't predict or prevent a Miyake event, we can only prepare. Harden infrastructure, build backup systems, design spacecraft with heavy radiation shielding, train crews for emergency procedures, accept that our technological civilization has a vulnerability we can't eliminate, only mitigate. The Quebec storm left 6 million people in darkness, and a $2 billion bill for grid upgrades. The Halloween storms left half our satellites temporarily lost, and transformers blown in South Africa. Solar proton events leave radiation damage in spacecraft electronics and elevated cancer risk for astronauts. Miyake events leave carbon spikes in tree rings and beryllium spikes in ice cores. The sun keeps throwing punches. Sometimes we see them coming, sometimes we don't, sometimes we barely notice, sometimes we nearly collapse. The disturbance storm time index hit negative 412 nanoteslas. Some readings showed negative 518 nanoteslas. Aurora displays reached as far south as 26 degrees magnetic latitude. People in Puerto Rico saw the lights. People in northern India saw the lights. People in Townsville, Australia, far from the poles, saw the lights. The storm lasted over 72 hours with multiple peaks as successive coronal mass ejections arrived. When the storm hit, extreme solar activity compressed Earth's magnetic field, dragging the plasmasphere inward. The compression was the most dramatic ever recorded by JAXA's Arase satellite, which has been monitoring the plasmasphere since 2017. The region remained depleted for over 4 days, the longest recovery period observed by the mission. GPS systems experienced complete blackouts lasting up to 16 hours during the worst peaks. Precision agriculture equipment that relies on GPS for autonomous operation reported erratic behavior. Some farmers described their tractors acting demon-possessed as GPS signals degraded. High-frequency radio communications failed across large portions of the planet. Airlines rerouted polar flights. Satellite operators placed spacecraft into safe mode to protect electronics from radiation damage. Power grids reported irregularities, but no major failures, a testament to hardening efforts implemented after 1989 and 2003. The return period for such events is approximately 12.5 years based on statistical analysis. That means on average, we can expect a storm of that intensity roughly once per decade. The March 1989 Quebec event was stronger by some measures. The Carrington event was stronger by all measures. But May 2024 proved that even with modern forecasting, grid hardening, and satellite safeguards, extreme space weather can still disrupt critical systems. Ground-level enhancements that penetrate deep into the atmosphere. And Miyake events, rare ancient superflares recorded only in isotope records that dwarf everything else. Each type has different physics, different speeds, different impacts. But they all share one characteristic: they're inevitable. May 2024 happened near solar maximum. The next big one could arrive tomorrow or 10 years from now. Forecasting has improved dramatically since Carrington's time. NOAA's Space Weather Prediction Center monitors the sun continuously with ground-based observatories and satellites like GOES, SOHO, Stereo, and Solar Dynamics Observatory. When a major flare erupts, alerts go out within minutes. When a coronal mass ejection launches, forecasters model its trajectory and estimate arrival time. Power grid operators receive advance warning. Satellite operators receive advance warning. Airlines receive advance warning. Multiple coronal mass ejections can merge in interplanetary space, creating cannibal events stronger than predicted. And for solar proton events, especially ground-level enhancements, warning times remain measured in minutes. The November 2025 ground-level enhancement caught forecasters by surprise with how quickly the particle flux rose. First, hardening infrastructure. Power utilities have installed devices to block geomagnetically induced currents. They've raised trip thresholds on protective relays, so minor disturbances don't trigger cascading failures. They've added series capacitors to transmission lines. They've developed operational procedures for reducing power flows during storm warnings. Satellite manufacturers use radiation-hardened electronics. They include redundant systems. They design spacecraft to survive total dose accumulations and single-event upsets. Airlines have procedures for rerouting flights during radiation storms. Machine learning algorithms are being trained on decades of observational data to recognize precursor patterns. Space-based observatories at the first Lagrange point provide continuous monitoring with typically 45 to 60-minute advance warning when a shock front arrives. Future missions may extend that warning time by positioning satellites closer to the sun or using coronagraph observations to detect coronal mass ejections earlier. Third, understanding the physics. Why do some solar flares produce huge coronal mass ejections while others don't? What magnetic configurations on the sun lead to the most energetic eruptions? How do particles get accelerated to such high energies during solar flares? What determines whether a coronal mass ejection will compress Earth's magnetosphere into a G5 storm or just cause a minor disturbance? Answering these questions requires both observational campaigns and theoretical modeling. NASA's Solar Orbiter, Parker Solar Probe, and ongoing ground-based studies are providing unprecedented detail about solar processes. Power grids need spare transformers stockpiled regionally since manufacturing lead times exceed a year. Space agencies need protocols for crew survival during extreme radiation events. The more layers of protection and redundancy we build, the more resilient we become. We could harden against Carrington-class storms. We could survive Quebec-class storms with minimal disruption. We can handle Halloween-class storms with operational procedures and advance warnings. But an event 10 times more powerful than Carrington, an event that leaves carbon signatures and tree rings detectable 1,000 years later, that would test every system simultaneously. Some things would fail no matter what. Lives would be at risk, especially astronauts in space and passengers on high-altitude polar flights. Economic damage would be measured in trillions globally. Recovery would take years, possibly a decade, for a complete restoration of all systems. Some produce superflares far exceeding anything the sun has shown in recorded history. Studies of other sun-like stars have detected flares hundreds to thousands of times more energetic than the Carrington event. Our sun is relatively quiet compared to many similar stars, but relatively quiet doesn't mean safe. It just means we've been lucky during the brief period when we had vulnerable technology. 10,000 years ago, a Miyake event barely mattered. Humans noticed unusual auroras. Maybe the lights inspired myths or religious interpretations. But there was no electrical grid to destroy, no satellites to damage, no astronauts to irradiate, no GPS to disrupt. 100 years ago, the Carrington event damaged telegraph systems but didn't bring civilization to its knees. 50 years from now, with Mars bases, lunar colonies, thousands more satellites, and even greater dependence on interconnected technology, the vulnerability will be higher than today. We need backup plans tested and ready. And we need to accept that space weather is a civilizational risk on par with earthquakes, pandemics, and asteroids. It's not a question of if we'll be hit again. It's when, how hard, and whether we're ready. The spike was twice the size of any Miyake event previously found. It confirmed that Earth has been hit by solar radiation storms far more powerful than anything in modern records. The trees remembered what we forgot. The ice remembered. The isotopes don't lie. The sun can unleash devastation beyond our current experience. It has before. It will again. And when it does, everything we've built that depends on electricity, satellites, and magnetic stability will face the test of its lifetime. The only question is whether we'll have learned enough from the small storms to survive the big one,